Welcome again to the Cybersecurity Seminar Series put forward by the UC San Francisco-Stanford Center of Excellence in Regulatory Science and Innovation, joint with the Food and Drug Administration. This is a distinguished speaker series for cybersecurity for biomedical engineering, and we'll be meeting every third Thursday of each month at this time at the URL below. So I have a couple welcome remarks. My name is Kevin Fu. I am the Acting Director of Medical Device Cybersecurity at the US Food and Drug Administration. And again, welcome to this seminar series kickoff. A couple disclaimers. First of all, this seminar series does not represent official FDA policy or guidance, and the content are those of the speakers and do not necessarily represent the official views of, nor an endorsement by FDA, HHS, or the US government. Also, this seminar is recorded. Be aware that this recording will appear on the UCSF-Stanford CERSI public website. So why are we here today? Cybersecurity is key for biomedical engineering and ensuring the safety and effectiveness of medical devices. And you can just look at the headlines over the last few years to see how significant this problem has grown, where cyber attacks are making medical devices unavailable to deliver safe and effective care for patients. And then earlier this year, President Biden issued an executive order on improving the nation's cybersecurity, in particular for operational technology or OT cybersecurity, of which medical devices fall into that area. So this speaker series is designed to, well, first of all, be presented by both the FDA and the UC California, San Francisco, Stanford CERSI. These will be a series of one-hour virtual lectures of distinguished academic speakers on cybersecurity engineering. So in particular, if you are a biomedical engineer, perhaps a student or a faculty member or an individual from the industry, we hope that these lectures will help you get a foothold in the cybersecurity engineering and science disciplines. You can better apply it to medical devices and medical products. A little bit about the UCSF-Stanford CERSI. You can read more about them on their website. Suffice to say, we're very thankful for our partners at the CERSI to helping us orchestrate this seminar and keep archives of it to help other people learn about cybersecurity for biomedical engineering. A little bit about FDA, and this is more for the archive, but if you'd like to learn more about FDA's activities on cybersecurity for medical devices, you can just search for FDA cybersecurity, and up will pop our landing page at the Digital Health Center of Excellence, where you can find many of our technical guidance documents and our communications about the importance of cybersecurity for ensuring safety and effectiveness of medical devices. A little bit about myself. Again, I'm Acting Director of Medical Device Cybersecurity at FDA, and I'm also on leave from the University of Michigan, where I'm Associate Professor of Electrical Engineering and Computer Science. It's my pleasure to serve as the moderator for this series. We have a number of very distinguished speakers coming up over the coming months. Here are a few of the upcoming speakers from Cornell, CMU, and the University of Cambridge and Edinburgh University in the UK. But it's my pleasure today to introduce Dr. Carl Landwehr. He is a visiting professor at the University of Michigan, and he has a long and decorated history in cybersecurity, leading cybersecurity programs. He's the former leader of the cybersecurity research programs at the National Science Foundation, dating back many decades, as well as IARPA, MITRE Tech Systems, and the Naval Research Laboratory. And in particular, he is one of the founding members of the National Cybersecurity Hall of Fame, which recognizes some of the top academic and influential cybersecurity researchers in the world. So it's my pleasure to have Carl speaking us today about a history lesson. I believe we're going to hear about 4,000 years of regulatory tales in a talk he's called Innocence and Experience, Regulatory Tales. A little word on housekeeping. We do not have a chat button. However, because of the size of the audience, we do have a Q&A button. So if you have questions, please do click there and submit, and then it'll go to the moderators. So feel free to ask questions throughout the talk. Without any further ado, I'd like to introduce Carl Landwehr now to present his talk, I'd love to hear about the last 4,000 years of regulations and how it might help us better understand how to apply cybersecurity to domains such as biomedical engineering.
So, well, thank you very much, Kevin, for that kind introduction. And I have to say, I'm proud but humbled to be at the head of the queue in this what looks to be an interesting series of seminars. I'll have to tune in for the other ones myself, I think. And I apologize for changing the title slightly on you. When I started thinking about this talk, I somehow thought I was going to work in William Blake, the poet, but that didn't work out. So my slightly revised title is Sparks, Carrots, and Sticks for these regulatory tales. The history of attempts to regulate technology is long and varied. So what I'm planning to do today is review some examples from a range of technical areas, some of which have been successful, some of which have been less so, and try to draw a few lessons from them. I've been advised it's a good thing to be able to put your entire talk on one slide, just in case anyone loses attention or interest. And so this is my attempt to do that. What I want to talk about today is how regulation of technology has developed in several different domains. I expect many of you in the audience are involved in designing or certifying systems that may be life critical in the biomedical domain. You probably know much more than I do about that specific domain, so I'm not going to say very much about that. I thought it might be interesting to spend a little time raising our eyes a bit to some different domains in which lives are at stake to see how regulation has developed over time in them. Each domain has got different characteristics. There are different industries involved, different public interests in the area, and politics often plays a role as well. Reviewing these examples, I hope, may help us understand how regulation in new fields like software development and cybersecurity might be structured and improved. So one of the earliest forms of regulation I'm aware of is a piece of Hammurabi's code. The entire code of Hammurabi contains 282 items that range from criminal activities to tolls for ferries and the prices of houses. But numbers 228 to 233 in particular concern the construction of houses. Section 229 shown here is perhaps the most dramatic, calling for the death of the builder in case the house he builds falls in on, kills the owner. If we think of this as a building code, it would be characterized as a performance code. It doesn't tell you how to build a house. It tells you if it doesn't stand up, you're liable for the consequences. So in effect, the builder warrants the building with his life. We must imagine these laws didn't arise without some stimulus. Houses must on occasion have fallen in, sparking the development of this code, which is surely in the nature of a stick. So if we look at building codes over time, let's look at a few more historical examples. They almost always, the changes are seeded, unfortunately, by disasters. So we could start with the Great London Fire of 1666. It was September 2nd through 5th on that year. It destroyed about 430 acres of London, which was about 80% of the city at that time. Documented by Samuel Pepys in his famous diary, it led to the 1667 London Rebuilding Act, which called for new construction to be faced with brick and imposed other measures designed to reduce the likelihood of large fires. Jumping ahead to the 20th century, consider earthquakes in California. The most famous, of course, is the San Francisco earthquake of 1906. A month after that event, scientists and engineers banded together to form the Structural Association of San Francisco and concluded that a well-braced wooden building secured strongly to their foundations could have withstood that quake. However, the city fathers declined to add earthquake resistance to the building code, and perhaps in order not to scare off developers, they blamed much of the devastation on fires. Ordinances were passed approving the use of reinforced concrete and requiring steel framing in any new brick construction. But it was not until 1925, when Santa Barbara suffered a severe earthquake that leveled most of its downtown, that requirements that structures be designed to withstand horizontal forces the first seismic code requirements entered the building code in California. Miami was hit by a powerful hurricane in 1926, and another category 4 hurricane struck a little further north in 1928 in the Lake Okeechobee area, causing thousands of deaths and severe property damage. Buildings made of brick or stone survived better than others, and this observation led to stronger building codes. As in California, only after the second disaster were the codes modified. Note, however, that the deficiencies in code enforcement led to severe damage from Hurricane Andrew in 1992, for example. So it's not enough just to have a code, you have to have the enforcement that goes with it. Now we get to ones that I remember. Collapse of the Hyatt Regency Hotel Skywalk in Kansas City in July 1981. A suspended walkway in the atrium of a large hotel collapsed under the burden of a large crowd at a Friday afternoon tea dance, killing 114 people and injuring more than 200 others. The case was ultimately determined to be a change from the original design in which the walkways were suspended. The change had been approved, but the fundamental problem seems to have been a lack of proper communication between the designer and the steel company. Responsible engineers were convicted of gross negligence and unprofessional conduct. They lost their licenses and American Society of Civil Engineer memberships, as did the firm that employed them. The Oklahoma City bombing of the Murrah building in April 1995 was, of course, a malicious attack by a domestic terrorist. It claimed 168 lives and damaged 324 buildings. The effect of this was to trigger construction of jersey walls around many existing federal buildings and to add new setback requirements for new federal construction. Finally, of course, we have the World Trade Center collapse in 2001. Again, a malicious attack, of course, but actually it's my understanding that the building design was intended to be able to withstand actually the attack that was made. So in 2004, New York adopted local law 26 with code revisions. And in September 2008, the International Code Council adopted 23 changes to fire and building codes motivated by lessons from that collapse. So let's summarize a little bit and review a few of the features. Note that a code can specify construction details such as what kind of materials are allowed on the outside of buildings. Alternatively, it can specify that the building will stand a certain velocity of wind without specifying how that's to be achieved. From the standpoint of sparking innovation, it's probably preferable to have a performance code. But you have to understand that if you have that kind of code, when there's new technology involved, you're going to have some way of demonstrating. You need some way to demonstrate that the new technology actually meets the specification. Also note that for building codes, inspections occur as the building is constructed, when the footings are poured, when the plumbing and electrical systems are put in, and so on. So part of a building code is not only inspecting the final building, of course, it's inspecting the building during its construction. So the design actually has to be approved before construction starts, that the design conforms to the code. And there are various inspections during the construction. And finally, you need to get an occupancy permit certifying the completed structure corresponds to the code requirements before the occupant can move in. So those I would characterize as sticks, largely speaking, but there are some carrots as well. First, the buyer and the financial institution that may have lent the money for the project gets some improved confidence in the product from the code conformance. And there's also some flexibility in that codes can be tailored to reflect local risks, earthquakes versus hurricanes, and so on, and they're enforced locally. They can evolve as technologies and conditions change, and that evolution can help build markets for new products. So I want to shift now to a different domain, aviation regulation. So you may not recognize this man, but he's Newt Rockne, the nationally famous football coach of Notre Dame in the 1920s. He traveled around the country giving talks, motivational talks, just as coaches do today, In late March 1931, he was en route to California to give such a talk. He took a train to Kansas City and then planned to continue by air to Los Angeles. His flight was actually on a Fokker F-10A trimotor, which sported plywood wings. The flight encountered bad weather near Wichita, but decided to proceed. But it subsequently crashed. The airplane crashed, killing all 8 people on board, and ultimately icing and failure of one of the wings was blamed for the disaster. This created a huge public outcry at the time, and all Fokker F-10s and F-10As were grounded. The history of aviation regulation is complex and well documented on the FAA's website and elsewhere, but there's little doubt that the aircraft industry itself played a significant role in creating and working with its own regulatory infrastructure. The industry realized that it could only prosper if air travel was seen as safe, and that the government had a key role to play in overseeing the safety of aircraft, pilots, and the air transport system. So the next slide is a little timeline, kind of showing some of the events in aviation regulation. Development of commercial aviation was intentionally stimulated by the Post Office Department, actually, which in 1925 started letting contracts to deliver the mail. And then subsequently, they added an additional requirement that mail contractors had to have the ability to take passengers on board. So this really started to create the airline passenger transportation to make it a profitable endeavor. The industry recognized from the beginning the need to establish public trust in the safety of aviation, and so it supported the idea that the Commerce Department would develop and enforce air traffic rules, license pilots, establish airways, and operate navigational aids. And that was all mandated within the Air Commerce Act of 1926. Nevertheless, there were continuing crashes, and those eventually sparked the 1938 Civil Aeronautics Act, which established the Civil Aeronautics Authority and its Air Safety Board to investigate crashes and recommend ways to avoid accidents. In 1974, the Congress moved in 1966, the National Transportation Safety Board was created. Right around here, I guess that is, as a separate body within the Department of Transportation to investigate accidents and recommend remedies. 1974, Congress moved the NTSB totally outside the Department of Transportation, making it independent. Importantly, the NTSB was not given any authority to regulate, so its recommendations had to be adopted by the FAA before they would have any force. The Airline Deregulation Act of 1978 was strongly influenced by the opinion at the time that government needed to regulate less, not more. But it's important to note that it deregulated airline fares. It didn't deregulate safety in any way. So the safety regulations remained. So I want to go a little deeper into this area. Because also around 1974, the industry started developing computer-controlled flight, basically fly-by-wire systems, so-called. And in this case, the computers are going to control aircraft in flight. So the developers asked the FAA what standards they would have to meet to get their design certified. And at first, the FAA just said, well, the flight control system should be just as reliable as the wings of the airplane. The wings shouldn't fall off and the flight control system shouldn't fail. So it should be, as in their terms in this memo, extremely improbable. But the developers came back and said they couldn't really build or meet to a standard of that was that vague and unquantified. And so they went back to the FAA. And
a question on your comment about probability. As you're moving from Mother Nature problems and building codes for Mother Nature more toward intentional, I'm curious if you can comment on the complexity of of probability and its appropriateness for cybersecurity metrics and such.
We're jumping ahead. Okay, I will get to cybersecurity later in the talk, but in terms of estimating probability, it's certainly people want to be able to estimate risk in some general way for cybersecurity for large scale systems. But as I know from your own talks, Kevin, where you have a malice involved and intention, it's hard to estimate probability. The probability of somebody blowing up a building in Oklahoma City would have been hard to anticipate in advance, for example. And right now, there's a pretty high probability if you put a system out on the internet, it'll be attacked. But just how it'll be attacked is open. Does that help?
Yeah. Let's continue.
So what happened in this domain actually was that's what they wanted, was a probabilistic measure of failure, because again, this is not considering intentional sabotage of airplanes. It's considering we're trying to build it and operate it in a safe manner. And so what ultimately happened is the FAA said, okay, we'll think about this, and they came back with another memo that said basically the failure rate should be by analysis no more than 10 to the minus ninth failures per hour of flight. And that seems to have come from an estimation that the longest flight at that time would be about 10 hours. And this meant that there would be only a failure one time in 100 million flights. And developers accepted that standard and they built to it. And today that the certification of flight control software is today governed by a regulation called DO 178C, which followed 178A and 178B, of course. And the most recent version was published in 2012. The next couple of slides give a quick overview of what's involved with that. One thing worth noting is that critical flight control software is subject to stringent controls to assure it won't contribute to a failure in flight. Since 2012, since 178C came out, formal methods have been specifically called out as an acceptable means for showing compliance with airworthiness regulations for software aspects of airborne systems. The inspection and certification is largely done within industry facilities by people closely involved with the software development and testing as FAA designees. We'll come back to that briefly. So DO 178 requires considerable documentation of software, which you're not likely to find in typical software development cycles, even though perhaps you should. And this software has to be documented in detail from the system requirements through high-level requirements all the way down to the source code and the object code. This overlay just shows some of the relationships that have to be demonstrated. I'm obviously not going to go through all of these, but it's just to give you the idea that in fact there's quite a lot of detail specified about what the developer has to demonstrate about the software design and implementation. And this slide just adds on the right-hand portion of the slide the additional requirements for testing and test results. So in this industry, you can see there's quite a bit of regulation, and it's generally been at least endorsed by the industry. A few words about FAA designees, okay? It was recognized a long time ago that the FAA might have a hard time recruiting and paying sufficient in-house staff to monitor aircraft manufacturers' designs and development processes. So a scheme was devised whereby the manufacturer would provide designated personnel, those are the designees, who would act as representatives of the FAA and be on the premises of the manufacturer, assuring that FAA documentation and standards were being met. This, of course, sets up a conflict of interest in that the personnel being paid by the company are in effect charged with overseeing people who are paying them. Nonetheless, the scheme has been in effect for decades, and it seemed to work. We'll talk a little more about that. So once the plane is fielded, of course, after the systems are designed and developed, there can still be accidents and near misses, events that might have turned out badly, but didn't by dint of good luck or good management. Accident and near miss reports can provide valuable feedback to both the FAA and industry on safety issues. But people might be reluctant to report such incidents because of concerns about personal and corporate liability and reputation. So this is the web page. Yep.
We actually have a question in that realm as you're getting towards sort of liability, and the question is wondering if whether two catastrophes are really needed, or if there's more to come before sort of new regulation is necessary, is how I would characterize it, especially for cybersecurity.
How many catastrophes?
How many catastrophes are needed in cybersecurity before?
That's definitely a hard question to answer for cyber. I think the answer is the number of catastrophes seemed, looking at these areas as a whole, if there are dead bodies around, that's a catastrophe. And cybersecurity, we've had a lot of things that I would consider catastrophes, but they generally haven't produced dead bodies. And my personal hope is that we don't have to have such a catastrophe in order to improve things. And I think we've had enough incidents of enough magnitude in cybersecurity that it is starting to have an impact, and I think we are starting to see some action. We'll get to that a little later, hopefully. So returning back to the aviation systems, one of the successes, I think, has been this aviation safety reporting system, which it's a scheme to encourage and enable the reporting of near misses. So the idea is, if you issue a report in this system, it's not attributable, and you can't be held liable for anything that you report. So one of the important things about this system, although it is an FAA system, it's actually set up and operated by NASA, which has no regulatory role. And so that gives people the confidence, I think, to make these reports. And there's a database that's publicly available for doing research on these things. It's provided by the ASRS. This system was actually put in place in 1976. Such systems had been thought about for a long time before that, but it took that long to get the mechanism set up properly. So we can't really talk about aviation regulation at the present time without talking about the 737 MAX. Boeing developed the MCAS maneuvering, that's the maneuvering characteristics augmentation system, which was designed to compensate for larger, more forward-mounted engines without requiring pilot simulator retraining. So the goal of MCAS is to detect an impending stall, particularly on takeoff, and to correct it automatically by using the horizontal stabilizers on the tail to push the nose down. Unfortunately, the system had a single point of failure. The angle of attack indicator, which the sensors are indicated in this picture on either side of the nose, they were redundant. There were two of them, but the MCAS system didn't compare the outputs of those two sensors. And so failure of one of those sensors actually could trigger the MCAS system to intervene during takeoff. If pilots could deal with this failure if they recognized what it was, but many had not been informed about the system. And so they didn't know how to respond in a chaotic situation. And that led to two very substantial fatal crashes. Was this, in the current context, was this a software failure? That's not the case, I would say, because software actually performed as specified and implemented. It was really a design flaw that should have shown up in the analysis of the design of the aircraft. Another question is, was it a failure of the designee system, since this was done really on the premises of Boeing? And I think that is quite possibly the case. The longer term effects on regulation from this particular accident, I think, are still in flux. So we'll see what happens.
Carl, as we're talking about the aviation, there was a question about how the aerospace near-miss reporting system compares to what FDA has internally is known as the MDR reporting system for medical devices. for adverse events. Now, I know you're probably not familiar with FDA's particular database, but certainly the databases are very different in the different OT or operational technology sectors. So maybe you could return back to this question as you.
So I am not very familiar with that system. I did hear an interesting talk several years ago by some people at Stanford, and I'm not sure if this is the same system. There's a system for reporting drug interactions. So this is not devices, but drugs, which basically accepts reports from the general public of, well, I took this and I took this and I had this side effect. And I gather that system has been widely considered by physicians as sort of useless because it was so open. But it turned out that these guys at Stanford were actually able to, by doing some clever data mining and looking at that, they actually were able to identify some real interactions. So I think, I guess the idea is having systems that allow some kind of reporting is a good thing. And if the FDA's got one for medical devices, I'm glad to hear about it. It may take some cleverness to make it effective and to learn from it. If we go back to aviation again and say, well, how well has aviation regulation worked? If you look at the safety record, I think you have to find looks like it's been pretty effective. These are just a couple of charts I found showing a number of fatal accidents per million flights going from 1977 to 2017, and then the number of fatal accidents per year with a 5-year moving average going all the way back 1946 to 2019. And so you can see pretty substantial declines in both of those charts. And I think that without the regulations, I guess you could say, is that attributable to the regulation or not? But I think it's a reasonable argument that it is. So quick summary of aviation, the sparks are accidents, that gets everyone's attention. The carrots are government certification. The government assumes the burden for doing all that. It all encourages passenger trust. And the aviation safety reporting system, I think, has been quite successful. There are some sticks, of course, the controls on critical software development. That's a real burden on the developers. They spend a lot of money on that. There's the ability to ground aircraft, deny licenses, and control operations. Now, when it comes to cybersecurity, really the aviation industry is just starting to address that, I would say. For a long time, and like many other domains, security was really handled by the fact that only trusted individuals had access to the systems, and the opportunity for hacking them was minimal. That situation has changed somewhat in recent years, and the FAA has begun to respond. By fall 2019, the FAA began to pay attention to explicit cybersecurity testing of actual aircraft, which they hadn't really done before. And the FAA has changed its internal organization. The air traffic operations organization at FAA now has a cybersecurity group within it, although it looks to me like that group is mostly focused on assuring the cybersecurity of FAA's own operational systems, navigational systems, and so on, as opposed to certifying aircraft cybersecurity. In October 2020, the GAO did a report called for strengthening the FAA oversight of avionics cybersecurity. I'm not sure whether those recommendations have been implemented as yet, but it does appear that DOT and the FAA is collaborating with DHS in cybersecurity. So just a few takeaways from aviation regulation. In general, regulation grew up with the industry and largely with industry cooperation because of a common interest in safety. Mechanisms supporting anonymous reporting of problems, near misses, and for investigating and understanding the reasons for accidents have generally worked well. As complexity of technology grew, centralized review of technical details was seen as impractical, and the FAA developed mechanisms to place trust in company personnel. That worked well as long as the companies maintained a strong safety culture internally. If you get away from that, then that kind of system can have problems. cybersecurity is a relatively new concern, and we'll see how that plays out in coming years, I think. Question?
Yeah, Carl, we have a number of questions, and there's going to be one here on aviation, but I think due to time we might have to skip over the automotive examples or go through quickly. But the question in aviation is, what about the concept of a presence of an adversary? And this is true, I can tell you for medical as well. There do exist adversaries, but I wonder the typical characterization of an adversary for aviation might be different from what it actually is. I'm wondering if you have any thoughts on what the actual adversary concern would be.
There have been reports I'm aware of a few people who took computers on airplanes and tried to hack in through the systems available to passengers to try to get to the control systems. And there were a couple of claims that people got through, but the aircraft industry in general denied this, and the proof was not made clear, I would say. So we don't know if anybody's actually succeeded at that, but there are definitely, I'm aware that one of the things that's some aircraft manufacturers have been looking at is wireless. You had fly-by-wire. Okay, now you're going to have potentially they're thinking about fly-by-wireless, and this concerns me greatly. Okay, because that would open up the control systems to wireless signals generated inside the fuselage. So I'm hopeful that they're paying attention to that. But in terms of the nature of an attacker, I guess from the military standpoint, of course, you might be concerned with someone in the supply chain attacking your flight control systems or any systems on board a fighter aircraft. So that could be quite a substantial and targeted attack. For civilian aircraft, I don't think that's probably thought about too much, but it's probably time to start thinking about it if they haven't.
Well, certainly it's, I'm always curious, which sector is the canary in the coal mine? Is it aviation, semiconductor manufacturing, medical devices? Certainly in the medical device realm, we see a large number of cybersecurity threats that are less traditional hackers and hoodies in their basement and more economically motivated, such as ransomware, where it tends to affect the classic property of availability rather than more traditional data privacy or things of that nature.
Right, and I think there have, I believe, I didn't look them up for this talk, but seems to me that one or two airlines have suffered outages in their scheduling and operations that were, I'm not sure if they were ransomware or other forms of attack. So that's an issue.
Yeah. Just, we do have a large number of questions, so we may have to speed through some of the automotive if we can.
Yeah, maybe I should just do a summary of this thing. The interesting thing about automotive is the contrast, in contrast with aviation, is that let's see. Well, this maybe is worth spending a minute on. The automotive industry, as opposed to the aviation industry, has generally resisted regulation. And initially that was, the idea was accidents were due to drivers, not due to cars. And so we should focus on driver training and driver education and not worry so much about other factors. It took, the trigger here was Ralph Nader publishing Unsafe at Any Speed. And also there was at the same time, if you look at, this is total deaths on the roads, there was a spike in that as well. And that ultimately triggered the beginning of safety regulation for cars. So let's see if I can skip ahead a few here. There's an interesting story to be told about actual seatbelts, but the bottom line, seatbelts were mandated to be installed, but they weren't used. And through an unusual combination of circumstances, it ended up that the auto industry was coerced into lobbying the state legislatures to pass laws mandating seatbelt use in the late 1970s. And a lot of states did pass those laws. And once those laws were passed, people actually did start using seatbelts much more often. And in fact, we're now up to the point where we're in the realm of 90% seatbelt usage. And a study that the National Highway Traffic Safety Agency, NHTSA, did in 2007 had a strong indication that the reason people were using seatbelts more in some states than others was they perceived it was more likely they would get a ticket. And so the lesson for regulation from that, I think, is that mandates can work. It took a long time for this mandate to have an effect, but it has had an effect over time. And so that's a possibility. This is a quick summary of automotive safety. So sparks are, accidents again, dead bodies really. And the sticks are that we have to regulate the auto industry are basically manufacturing requirements to install equipment, enforce mandates, lawsuits, and recalls. You can also have recalls, which are quite expensive for the industry. The carrot for the industry is probably minimal. They can attract safety-minded customers, and they can, of course, try to avoid the sticks. So that's a sort of a carrot. I wanted to say something briefly about automotive emissions. So you had air pollution more generally, but in the 60s, some of us will remember the Cuyahoga River actually caught on fire, which was a dramatic evidence of the kind of pollution that was going on. Didn't have to do with automobiles. But the point I would fast forward to in the automotive discussion for emissions is the VW diesel emission scandal, because that really, what happened was in 2006, VW recognized they had a problem. They had high mileage diesel engines, but they had difficulty meeting standards for reducing emissions of nitrous oxides. So they thought they had a cheap solution, but it didn't work in practice. So instead of investing in more expensive technology to clean the exhaust, they decided to game the system. So they introduced engine control software that would run the engine in a low pollution mode when it detected the conditions under which the EPA would test the engine, but in a different high pollution, high mileage mode when the car was actually driven on the road by customers. So this was referred to as a defeat device, which really in effect was a Trojan horse in the engine control software. The scheme was effective for Volkswagen for several years, but it unraveled when a West Virginia University researcher who was under contract to the California Air Resources Board measured actual tailpipe emissions on the road in 2014. So they got 6 years or more worth of use out of this defeat device. But they've lost billions of dollars now in fines and scandals, but they still remain one of the top 2 auto manufacturers in the world. So I think this highlights the fact that you need to do testing. First, software-based products introduce hard to detect possibilities for fraud. And observing product behavior in the real world is the acid test. The lab testing was never going to catch this because they had gained that. And so what that says is it may be necessary to gain visibility into the software during development, as is done, for example, in aviation, if you want to have high assurance about it.
So Carl, just a time check. We have about 1 more minute before we'll have to turn to the questions.
Oh, wow. Okay. So the whole cybersecurity part of this, there's a long section. These slides will be available, and I'll be happy to make the notes available too if people want them. But the history of regulation in cybersecurity is maybe captured on this slide to some extent, at least the early history involving the Orange Book. And the idea of the Orange Book was to have something which would provide if you will, consumers reports like structure for reporting on the security of systems. And the incentive then was that the carrot was the government would buy systems that specified higher security levels. There were a number of difficulties in getting this scheme to work. Evaluations tended to take a long time. And there were reasons for that. Partly looking at the software took time, but also if you found a problem, then it was up to the vendor who was developing the software to fix that problem. And at the same time, the government requirement for competitive procurements caused a problem because initially there weren't very many evaluated products. And so if you wanted to have a competitive procurement, if you specified that the product had to meet a certain level of evaluation, you would get dinged for being non-competitive. So it meant that they decided the way around that was to say, well, if the product is aimed at a certain security level and in evaluation for that level, we'll consider that it can be in the competition. And that meant that manufacturers had a perverse incentive to enter the evaluation cycle, but not to complete it. And that dragged things down too. And the structure of the criteria had some problems as well. Nevertheless, that scheme is still to some degree in effect with the common criteria now. And I think the difficulty with the common criteria evaluations that we see is that they very rarely involve actually looking at the software. They're looking at documentation about the software, and that documentation may in fact even be created separate entirely from the creation of the software. So real cybersecurity problems tend to be in the actual software, not in the documents around it. And so it's not clear to me that those evaluations are very effective, even though there are a lot of companies willing to do them for you. A few notes on cryptography. Yeah, you want to stop here?
I know you're going to make your slides available, and because of the time constraints and because of the number of questions, I think we'll have to turn to some of the questions now, and maybe you can channel some of your slides in those responses, if you don't mind.
Sure.
But we have a question dating back to one of the aviation issues. You mentioned DO, I believe, DO 178C applies to all software involved in aircraft flight control. That is both the control application as well as the underlying operating system, which is usually a real-time operating system, which you'll find real-time operating systems in all sorts of medical device and biomedical engineering products. But in the medical world, there's an increasing emphasis on the use of static checkers. So I assume this means static analysis for security that usually only applies to the device. So if the underlying operating system is something like Windows or Linux, the question is to create high assurance medical devices in this case, should they be built on high assurance operating system platforms, or is it possible on commercial operating systems like Windows and Linux? What are some of your thoughts on that question?
I would be inclined to go for the high assurance operating systems rather than the Windows and Linux, but you inherit a tremendous amount of software code in those systems, much and a fair amount of legacy code, whereas the high assurance real-time systems do exist, and I would encourage people to leverage those.
Right. Okay. We have the next question from Adam. He asks, what mechanisms are there to detect or report software failures in deployed systems, and how reliable do you think they might be? I know that's a simple question, but it can get rather complicated when you talk about the US government has, I believe, on the order of 20 different risk management sectors, everything from transportation to food, medical devices, health. But what are some of your thoughts on how to detect and report software failures on deployed systems? What might be recommended? What works well?
Well, so I think you're referring, Kevin, to the critical infrastructure sectors, of which I think there are 16 or 17. And each of those sectors has what do they call them? Information sharing and analysis centers, ISACs. And so if the problem you detected falls in one of those critical sectors, you could look for the ISAC in that area and report it that way. I'm not sure those ISACs, a few of them have been quite effective, I think, financial sector and some others, but not sure about the other ones.
So
I don't know that there's.
Go ahead.
So actually, the slide that I'm hoping that you're seeing right now is the cover of a report that just came out in the last couple of weeks, which was the result of a workshop which was trying to look at what if you tried to create a National Transportation Safety Board equivalent for cyber incidents. And the idea here would be if you had a major cyber incident, solar winds or whatever, could you have an independent body set up to actually investigate those things and draw the lessons out from it? And this is that's an idea that's been floating around, as this report says, since 1991. But nobody's ever really taken it seriously and taken it to the next step to look into it. And this report made an attempt to do that. And I think if we could set up such a thing, that would be the place to report. The place to report today, I'm afraid, is as you've observed, it's fragmented. It depends on the system that you're involved with and find a difficulty with.
So I can tell you, at least in the public healthcare sphere, there is a group that's highly applicable to anyone in biomedical engineering making a product, primarily used by health delivery organizations and medical device manufacturers, called the HISAC, Health Information Sharing and Analysis Center. They put out regular bulletins on threats, and they're able to do so in a way making use of certain protective government orders, so you can share things in a manner in a gradual way. So for instance, when a vulnerability is discovered, can be shared with some of the key stakeholders responsible for repairing it before announcing it to the world, so that they have time to develop, for instance, their patches and changes. There's also something called the Healthcare Sector Coordinating Council, the HSCC, and they actually produce, it's not regulation, but they produce many, what I would consider consensus documents written by health delivery organizations and medical device manufacturers from the engineering side of the house primarily, for certain topics in cybersecurity that are just really key to the next, I would say, 5 to 10 years. In particular, there was a document recently released on legacy software. How do you handle legacy medical devices out in the field that perhaps are built on unmaintainable Windows 95 operating systems, right? Good luck regulating and certifying something that is insecurable when those systems don't even have patches available anymore. But I would encourage anyone with questions about reporting to look at the HISAC as well as the HSCC. They're quite friendly with allowing new members if you have a bona fide interest in the manufacturing of biomedical engineering devices, and it's probably a good place to start. Let's see. I see another question here on less on regulation, but there's a question on along the lines of non-punitive confidential reporting. What are some of your thoughts on coordinated disclosure processes? I can certainly tell you about what FDA does on coordinated disclosure, but maybe you could give us some of your thoughts across the different sectors.
So I presume that's presuming that if you find a vulnerability, how do you responsibly report that?
Yeah, or say if you're a manufacturer of some kind of biomedical engineering device, and maybe it's a security firm, maybe it's, it could even be like a college kid who just discovers a flaw and sends you a single email. Some of these come in the most bizarre ways. I've received coconuts in the mail with messages. And FDA has a large number of different pathways to receive information about vulnerabilities that have to be vetted. But to a manufacturer or to an engineer who's relatively new to cybersecurity and maybe even doesn't have the same definition of cybersecurity, IT versus OT. Curious about some of your thoughts in the final moments of our session here.
I don't know that I have any real novel ideas in that area. I mean, I think that it's clear that you don't want to, just post it on a public bulletin board. What you found, you want to provide it to the person who's in a position to fix it. I mean, I think that's the number one thing, and that person needs to accept and be willing to investigate the problem and make a decision as to how to fix it. And there should be some timelines on that, some deadlines. But there's also a question that if that's place the vulnerability is found is a product that's incorporated in other products, there's clearly a need for coordination with the other vendors that are downstream in the pipeline. So that was certainly the case for SolarWinds, for example.
All right. Well, I see we're at the top of the hour. I'm wondering if you might have any final thoughts. Again, this is a community of biomedical engineers, and although this is not about biomedical engineering, it's about cybersecurity and what biomedical engineering can learn from some of the incidents in the other sectors on cybersecurity and how to better integrate it into their work processes.
Well, so here's my silly conclusion. Okay, the public is like a dog that mostly prefers to sleep. Okay, it can be aroused. If there are enough fleas out there, if there's some sparks that get it going. If it does, the public is the dog, and the regulators are the tail, and the public is going to wag the dog, not vice versa. But I think it's true that with the right incentives, industry will develop products meeting broad public needs. But vigilance is required. Okay, so this is a pretty simplistic, but what I would encourage biomedical engineers to do is think about the incentives that are in front of the manufacturers and how to make incentives that will actually lead to systems that have fewer vulnerabilities in them in the first place. The place that we've gotten ourselves to today is not, in my view, a good place. We're in a place where it's continual patching and updating, and you're never really feeling very confident about the system that you're running. And that's not a good place. We need to be in a better place than that. And I think the real way to do that is improve the engineering of the products up front. And we have to figure out how to provide the incentives to companies to do that. And we've done it in aviation, perhaps, and somewhat in automobiles, although there are some real questions there today. We certainly need it in our medical devices.
Right. Well, thank you for these perspectives. I think the only thing missing from the sort of academic history talk would be the leather chairs in the giant lecture halls, but we'll have to make do with the Zoom protocols of backgrounds and such. But thank you so much for taking the time out of your day, Carl, for introducing some of the concepts of cybersecurity and history of regulation as we try to learn from other fields to see how we can better incorporate thoughts in engineering and science practices.
Thanks very much for inviting me.
Right. Thank you, Carl. So this ends our session for today, and we will resume again in a month. Our next speaker will be Fred Schneider from Cornell, who's going to talk more about the science side of cybersecurity and how to measure it. And what are some of the fundamental, essentially, physical laws of physics for cybersecurity so you can better bring it into your metric systems. Thank you all for joining, and this concludes today's seminar.